All right, so let's continue with our observations. The third one is the following. So let U be any tangent vector, be any unit tangent vector, and P be a plane, be the plane through the point P containing U, the vector U, and the normal vector of the surface P. The intersection of M with P is a curve through P yes. Let me first write this and then I'll explain on a picture. Let sigma be a unit speed parameterization of this curve. Okay, so let me now draw a picture. I have a surface. Okay. Let's say a surface like this. M. And we take a point and a vector U, unit tangent vector, and I have my normal vector to the surface at that point, and we look at the plane through this point containing both these vectors. There's a unique plane, of course, going through this point and containing these two vectors, right? Let me draw that plane here also. So a plane like this. Okay, let me draw the curve, maybe with a different color. Okay, so the intersection of the plane with the curve is something like this. Okay, so this is maybe that line. All right, and I take a parameterization for this, a unit speed parameterization for this curve, sigma. Okay. Of course, this curve is the intersection of the plane. Plane is, let me say, plane is gamma. So my curve is basically image of this curve is what? It is M intersection with gamma, right? Surface intersected with this plane is my curve. All right. Well, since I choose a unit speed parameterization, the tangent vector to this curve at this point will be a unit vector in this direction, but that direction is already the u direction because my plane contains that vector. So u is nothing but alpha prime, not alpha, sigma prime 0, sigma prime 0. Yes. Okay. And normal to this curve, let's say, so this is the point P, normal vector to this curve is, let's say, this one, and P, normal vector, and the angle between the normal of the surface and normal of the curve is nu, okay? So let me write them down also. Okay, şeyi değiştirmedim. N is the principal normal vector of the unit speed parameterized curve sigma. Okay. All right. So what do we have here also? Okay, now sigma is a plane curve, right? Sigma is a plane curve. Therefore, its normal vector also lies in the plane P, right? This is a curve in this plane. Therefore, its normal vector also lies in this plane. So my picture is not correct in that sense, right? Right? If you have a curve on a plane, its normal vector lies in the plane. It cannot go out the plane. So this n is then actually should be in the plane, and n is perpendicular to the tangent vector. Tangent vector is this. It is the vector u. Therefore, so this angle has to be 90 degrees, but this vector also should be in the plane. Therefore, this NP is either this vector or this vector. So this angle has to be 0. This angle has to be 0 or 180. Okay. So let me write that down. Since n must lie in the plane gamma and n is perpendicular to u, which is alpha prime 0, we must have
Hocam kamerayı görebilirsiniz. Teşekkürler.
Okay. All right. Since n must be in the plane gamma and the normal vector of the curve is perpendicular to the tangent vector of the curve, we must have either n is equal to u or n equals minus u, right? Because you see, this is my plane gamma, and here is my u vector alpha prime 0, and I have the vector u, which is in the plane and perpendicular to this vector, and n is another vector in the plane perpendicular to u. So there are only two unit vectors perpendicular to u in this plane. It is either this vector or it's negative minus u, right? Okay, so what we have done, the normal curvature along u is by definition, not by definition, but we know that this is just the second derivative of the curve, the acceleration vector, times the normal vector of the surface, unit normal vectors of the surface, and we computed that this is just the curvature of the surface times the normal vector of the surface, or p, right, times up. But this vector is either this one or it's negative. Therefore, this dot product is plus minus 1. If they are in the same direction, it is 1. Otherwise, it is minus 1. So what we get is minus this. So the conclusion is that if your curve is obtained by cutting the surface with a plane, then the normal curvature of the surface in the direction u is the tangent direction to the intersection curve of the surface with the plane, is equal to plus or minus the curvature of the curve you obtained by intersecting the surface with the plane. Tamam mı? Okay. So it's a very geometric description of this expression, right? What is this? You just cut your surface with the plane containing both the normal vector of your surface and the vector you are given. You obtain a curve. The curvature of that curve at the point P is the normal curvature. It's either plus or minus that expression. But note that this plane is not an arbitrary plane. It should contain also the normal vector of the surface. So it should be perpendicular to the tangent space. And tangent space, if this is your tangent space, then this plane gamma should intersect it vertically. Okay, it's something like this. It cannot be like this. Yeah. Okay. All right. Some observations. We have already done some observations, but these are some more. If the normal curvature of your surface is positive, then you know, I am assuming the above setup and 0 or and okay. Here is, of course, I am, considering the same situation here. So we have a plane, and so this is my point P, this is my sigma, and so on. Okay. Then so the normal section sigma is bending toward UP at P. So if UP is, let's say, this vector UP, in this case, actually, it is the opposite, right? The curve sigma is not bending toward UP. It is bending toward minus U. So in this case, curvature is negative. Okay, in other words, in the direction U, of U, the surface is bending toward UP. If it is negative, if curvature is negative, then so this is the second observation. Then we have the opposite. Then NP is minus UP. So the surface in that if the curvature is positive, your surface is like this, okay? And this is your normal vector, and your surface is bending toward this vector. If the curvature is negative, then your surface is like this, as in this picture, and your normal vector is like this, okay? Of course, everything just goes upside down if you choose the other normal vector field, right? If you choose this normal vector field, this is what's happening, but you may choose this normal vector field, then this curvature will change sign, okay? If it is positive for one direction of U, it will be the other one, -1 times that curvature, if you choose the other unit normal vector. Değil mi? İki tane unit normallığınız var. Bunu da seçebilirsiniz, bunu da seçebilirsiniz aşağıya doğru gideni. O zaman da bu sonuçlar tabii -1 ile çarpılacak. Birindeki pozitif, diğerindeki negatife dönecek. Okay, so so the normal section sigma is bending away from UP at P. Thus, M is bending away from you. So it is like this one, okay? In this case, surface is like this, unit normal vector is like this. So your surface bending away from this normal vector, okay? All right. If, so this is the third one. If this is 0,
Hocam
okay.
kamerayı yine açın.
If this is 0, then okay, no, if okay. Yeah, I should write if Ku is 0, then this is also 0, and 0 is undefined, or NP is undefined. Why is that? Because NP is the unit normal vector in the direction of the acceleration vector of the curve sigma, but the second derivative is 0 means the acceleration vector is 0. Since the acceleration vector is 0, you don't have a normal vector, because normal vector was the acceleration vector divided by its length. But this guy is this gadget, and this is 0, therefore NP is undefined. And since this is undefined, okay, so let me write hence the normal section sigma is not turning. So in this case, we cannot say whether it is bending towards the normal vector or away from the normal vector. It is undefined. Here is an example. Let's consider this surface z equals xy. Okay, so let me draw a better picture. Yani bu da daha iyi olmadı ama neyse. Okay, so now there are these curves. Okay, consider this point. I can cut through with a, and this is our surface normal U at this point. I can cut it this with a plane containing the vector which is perpendicular to the blackboard and this one, and I will get this curve. Let's say this curve is gamma 1, gamma 1. I can cut this surface with a plane, right, with the blackboard, and in that case, this will be my curve. Let's say gamma 2. Gamma 2 is this one, is this curve. And then I can cut it with this planes. So I have two planes cutting this surface again. One of them is, okay, plane like this. We cannot see the other part because it is, bending. And this is, let's say, gamma 4. And I can cut it like this, and we obtain a curve, gamma 3. Gamma 3 and gamma 4 are actually lines. So gamma 3 is this line. It is the intersection of the surface M with the plane gamma given by, okay, let me see. Z equals 0. Bir dakika. Gamma hangisi? X'in 0 olduğu yer. X 0. Yani şöyle o zaman bizim şeyimiz bu y ekseni şöyle bir yerde x ekseni var. Şu da z ekseni. X, Y, Z. Belki şöyle hatta. Y. Okay. So gamma 3 is this. Gamma 4 M intersection with the plane given by y is 0. So this curve is what? Gamma 3 is the curve. Actually, it's a line. This is the line. Z is 0 and X is 0. And actually, you see, when you plug 0 here, if you are on the surface, then Z must be 0. So both Z and X are 0. So this is just the Y axis, right? X and Z are 0. So this is just the Y axis. And this is the line. Z is 0 and Y is 0. And this is just the X axis. So this surface contains the coordinate axis, X and Y. So this is the X axis. No, that's the Y. This is the X. Yeah, right. X axis and Y axis. This is X, this is Y. What about gamma 1 and gamma 2? Yeah, one of them is, they are both parabolas, right? Let's see which one is which. Gamma 1 is M intersection gamma, and gamma is the plane given with this equation, y equals minus x. Therefore, gamma 1 is the parabola. The parabola given by y equals minus x. And when y equals minus x, we get z equals minus x squared. So z equals minus x z squared. So it is this one. Okay. So this is z equals minus x squared. In the plane, y equals no, x plus y equals 0. So also y is minus x. Since it is a curve, I have to describe this using two equations. This is the plane, x plus y is 0, and in that plane, it is z equals minus x squared. And the other one, this one is what? This is the other parabola. So again, it is, so, okay, let me write. Yeah, this is just y equals x and z equals x squared. So gamma 2 is M intersection with the plane y equals x. So gamma is given by these equations, x equals y and z equals x squared. Okay. Again, a parabola. So this is a strange surface, right? This surface contains two parabolas and then two lines. Okay. Intersecting two lines. Actually, they are just coordinate lines. Okay. And if you okay, now what about the curvatures? Normal curvatures. Along gamma 1, gamma 1 is this curve, and it is going away from, right? It is bending away from the normal direction. Therefore, so if I choose this vector as my unit normal to the surface, I could choose also this one, okay? It's up to us. But if I choose this one, then along this gamma, my surface is bending away from you. Therefore, the curvature is negative, right? So along gamma 1, K is the normal curvature. Is negative. Along sigma 2, this time the surface is bending toward you. Therefore, the curvature, normal curvature, must be positive. The normal curvature is positive. What about the other ones? They are lines, right? For a line, curvature is 0. And the curvature of the curve and the normal curvature are given like this, right? So along a line, this normal curvature, not normal curvature, I am sorry, the principal curvature is 0 for a line. Since this is 0, this normal curvature is 0. So along sigma 3 and sigma 4 along sigma 3 and sigma 4, the principal curvatures, the curvature of the curves are 0, and hence the normal curvatures are 0. Okay. All right. For a ruled surface, well, actually, this is ruled surface. So along lines, curvature will be 0, but along other axes or lines or directions, curvature need not to be 0. For a cylinder, again, you know, for a cylinder, if you cut it like this, normal curvature will be 0. But if you cut it like this, then the curvature won't be 0, right? Because the curvature of the circle is positive. So if you just cut, with a perpendicular line to the cylinder, you will get this, horizontal circle, and the normal curvature of the surface will be just plus or minus the curvature of the curve, and it is just 1 over r. So it will be either plus 1 over r or minus 1 over r, depending on whether you choose this normal vector to your surface or this normal vector. Okay. We have a definition. Let me write that down. Let P be a point of the surface M, which is contained in R3. The maximum and minimum values of Ku of M at the point P are called the principal curvatures of M at P. And they are denoted as K1 and K2. So K1 is the maximum value of the normal curvature. K2, no, K1, yeah, K1 is the maximum, K2 is the minimum value. Okay, so for example, for this example, well, I didn't compute, of course, the curvatures, but yeah. All right, one of them was positive, the other one was negative. So K1 is the curvature of the this parabola. So sigma 2, and this will correspond to curvature of sigma 1. The directions in which these curvatures, these extreme values are obtained or obtained are called principal vectors. Vectors of M at P. Okay. Another definition. If Ku is constant on a tangent space TPM. So you have a surface and you compute curvatures, normal curvatures at the point P. You choose a direction, you compute the curvature. And you see that you get always the same number, okay? In that case, we call that point P an umbilic point. Then the point P of the surface is called an umbilic point. Neredeydi o? Of M. Okay. Yes, actually that's the example I would just give. So consider a sphere of radius r, let's say. R, radius r. Choose any point P. So if you choose any vector tangent to the surface at this point, let's say U, tangent to this one, and consider the plane containing this and the normal vector to the surface at the point P. The normal vector to the surface is just this vector, right? Let me choose the outer normal. This is the normal vector, and this is any tangent vector. How would you compute the curvature, normal curvature along this vector? Well, I know that if I take the plane passing through this point containing this vector and this vector, then the curvature of the intersection curve is equal to this gadget, plus or minus this gadget. So what is that plane? So I just take the sphere and consider the plane containing this point and the vector u. That vector is the vector joining this point to the origin, right? So I am just taking a plane, cutting the sphere so that the plane contains the center of the sphere Okay, and this is the curve of intersection. uh, this is the tangent curve. So what is that curve? If you cut your plane, sorry, sphere with a plane going through the center, then the intersection is a great circle, right? So this is a circle. Yes. Sorry? But plane should contain the normal vector, and the normal vector joins this point to the origin. And my plane contains this point, and it contains this vector. So if you go along that vector, you will reach the center. So you don't cut your sphere with an arbitrary plane. You cut your surface sphere with a plane going through the center. And what you get is a great circle, not just an arbitrary circle, okay? A great circle with maximal radius, which is r. And so this is a I am sorry, this is a circle of radius r. And what would be the curvature? Well, this is plus or minus the curvature of the surface, right? Sorry, of the circle at this point. And what is that curvature? Curvature of a circle of radius r is 1 over r, right? So this is just plus or minus 1 over r. Which one? Well, it depends on how you choose your unit normal vector. If I choose outer normal, the curvature of my curve, right? If you take a circle like this, the curvature goes inside the circle. Therefore, my curvature, my normal vector to the circle is going in the opposite direction. So u is like this. So in that case, I should choose the -1. So for a for a circle, for the sphere of radius r, the normal curvature along any direction is -1 over r. If you choose your normal vector outer normal. If I choose my normal vector inner normal, then it would be +1 over r. In particular, all the points of the sphere are umbilic points because the normal curvature function is constant. It is 1 over r or -1 over r along any direction. So k is constant at any tangent space. Hence, all points of the sphere of a sphere of any sphere are umbilic. Do I have time? No. Okay. But let me just give you this example real quick. Okay, choose any point on a cylinder. And let's say this is my outer normal vector. So u is my outer normal vector. And what I do, I take any direction here, any direction, and consider the plane containing this point, this vector, and one of these vectors, any one I want. So what happens is this. This is my cylinder. Okay, this is my cylinder. And here is the point. And I cut this cylinder with a plane. I can rotate this plane in any direction I want. If you cut it like this, then you get a line, and curvature will be negative, right? Curvature will be 0. Sorry. So if you choose this vector u, let's say u1, curvature will be 0. If you cut it like this, the intersection will be just this circle, and its curvature will be 1 over r. So if you cut it like this will be 1 over r. But since I choose my, again, normal vector, outer normal vector, this should be minus 1 over r. And if you cut with another plane, not necessarily, this perpendicular plane, you will get an ellipse. And the curvature of the ellipse will be, I guess it will be something between, right? I mean, so it will be a circle, ellipse like this. Yeah, I guess it will be something between 0 and 1 over r. So this will be the minimum value. No, in this case, it is the maximum, and this is the minimum. So these are the principal curvatures. So if you choose any other direction, ku, it will be between minus 1 over r and 0. So this is the maximal value. This is the minimal value. These are the principal curvatures. And principal directions are u1 and u2, right? Principal directions are this one and this one. Okay? All right. Work on the problems suggested in the syllabus so that you get used to this, notation and the concepts. Otherwise, everything will evaporate in a couple of weeks. So you won't remember anything. So just work on some problems. All right, so let's stop.